All right, let's talk about free fall, and we'll do some free fall problems here. Once again, a reminder, 9.8 is actually the right value for that, but we're going to use 10 just to make it simpler. A couple of formulas that you need to be aware of. First one right here, distance equals, and then VO stands for initial velocity and time. And I'm going to delete, the little triangle stand for delta, they stand for the change in. And I'm just going to take them out of there for the sake of not having to have such a long formula. Plus 1/2, and I like to use AT squared because I just think that's a generic formula. I like to use it. Now what we did, our equation just a little bit ago, or what you did in the book, looked like that. Distance equals 1/2 AT squared. All we're saying is we're adding in, if we've got an initial velocity, we do need to take that into account. And that's what that is. But if this velocity is 0, which in almost all the cases that we do, it's going to be 0. Most of them are 0. And then it just boils down to the old formula that we have. Here's another new equation. And we're saying that the final velocity squared is equal to my initial velocity squared plus 2 times acceleration times distance. And typically, when we do that, we want final velocity, obviously. And so we'll take that to be the square root of the initial velocity squared plus 2AD. And once again, since often initial velocity is 0, that boils down to final velocity equals the square root of 2AD. And that's a pretty common physics formula. And notice that in order to, what we're doing is we're trying to find a final velocity, and if we know acceleration, we know distance. So if we know those kind of things, then we can figure that out. So that's what we're kind of trying to figure out on that one. And then we've got this formula, final velocity equals acceleration times time, basically is what that is. So we've got final velocity. Well, if we had any velocity to start with, that would be my initial, and acceleration times time. And what we had done prior was say velocity final equals acceleration times time. That's the formula that we used in the book. So they're slightly different. They look a lot more complex, but really they're not. Don't get all worked up about all that. Most of the time, these things are 0. I mean, I would say probably 98% of the time that we do problems, we're not going to have initial velocities. But on the occasion that you do, this is the formula that you would use to do that. All right, let's go through some of these sample problems. King Kong carries Fay Ray up the 321-meter tall Empire State Building. At the top of the skyscraper, Fay Ray's shoe falls from her foot. How fast will the shoe be moving when it hits the ground? All right, so let's talk about what do we got. Well, we know that initially there is no velocity of her shoe. It's falling off her foot. So acceleration due to gravity is 10, and our distance is 321 meters. So what's the equation? Well, this is the equation that we're going to try to use. We have distance, we have acceleration. So we're looking for an equation that gives me a velocity, because it says how fast, what's her final, fast is velocity, and we want to know what the final velocity is. So we're trying to find that. That's my unknown. And we're going to have to use this equation right here. But since this is 0, we don't have to worry about that. So we can say it's final velocity squared equals 2GD, or final velocity equals the square root of 2GD equals the square root of 2 times 10 meters per second squared times my distance is 321 meters. So if I calculate that out, let me do that here just a second here. I am going to get square root of 6420, which would be approximately 80.1 meters per second squared. So a little bit of a new formula there, a little bit twist to it, but just plug in the things. It's not too bad if you have to do that. And like I said, this looks a little confusing with all the V0 stuff, but most of the time it's 0, and so then it's not too bad. All right, number 7, the Steamboat Geyser in Yellowstone National Park, Wyoming is capable of shooting its hot water up from the ground with a speed of 48 meters per second. How high can this geyser shoot? Well, let's think about it. We're trying to shoot it up in the air. It's going to go up at an initial speed of 48. It's going to go up, eventually stop, and then it's going to come back down. That's kind of how things work. So it's shooting up, and since in this book, up is considered to be a negative initial velocity. To be honest, that's an arbitrary decision on anybody's part when they do these. But for convention, to make things the same, we're going to say that the upward velocity is negative 48. So here we go. Here's what I know. I know the velocity going up, 48 meters per second. Final velocity is 0. My acceleration due to gravity is 10 meters per second squared. And I want to know the distance. That's what I'm trying to find here. So figure out which equations that would work. Well, here's the equation. I've got a final velocity. That one happens to be 0. I've got, this time I do have an initial velocity of negative 48. And I know G, that one's easy, and I can solve for D. So that's my original equation. If I start plugging things into this now, I'm going to get 0 for my final velocity, 0 squared, 0. And I'm going to get negative 48 meters per second squared. And notice that now it doesn't really matter that you put it in negative. So, that didn't matter here. 2 times 10 meters per second squared. And we're solving for D. So if we calculate out what we've got here, hang on a sec. Calculate, get my calculator again. 48 squared, that's 2,304 plus 20D equals 0. So let's take that to the other side. Negative 2,304 equals 20D. And if we divide both sides by 20, D is going to equal negative 115 meters. And remember that according to our convention, we said that up was negative, so it's 115 meters up in the air is how high that's going to go. Okay. All right, let's go to the next one. Okay, a baby blue jay sits in a tall tree awaiting the arrival of its dinner. As the mother lands on the nest, she drops a worm toward the hungry chick's mouth, but the worm misses, falls from the nest to the ground in 1.5 seconds. How high up is the nest? Well, all right, let's take a look at what we know. Well, we know the worm wasn't moving at first. So 0 initial velocity, gravity 10. And the time is 1.5 seconds. So we want to figure out, we want a formula that involves distance, because that's what we don't know, acceleration, and time. Okay? So distance, acceleration, and time. So if we look at our equation, if we just remember distance equals 1/2 AT squared, that's the one I'd like you to remember. Okay, and plug in what we know. We know that we're trying to find the distance. We know that is 1/2 times 10 times 1.5 squared. And if you multiply that out, you're going to get 11.3 meters. All right, one more. All right, a giraffe who stands 6 meters tall bites a branch off a tree to chew on the leaves, and he lets the branch fall to the ground. How long does it take the branch to hit the ground? So what we're trying to figure out is the time. Okay, so we know that he's 6 meters up. We got 10, and once again, it didn't start with anything, so initial velocity is 0. We're trying to find time. So we need a formula that involves distance, acceleration, time, and we've got it. And that is distance equals 1/2 AT squared. But we want to solve for t, which, you know, it's a square term, so that makes it a little bit weird. So let's just kind of go through the math here. If we get rid of the half, multiply both sides by 2, we get 2d equals AT squared. Now let's divide both sides by a, and we get t squared equals 2d over a. And if we solve for t, so we take the square root of both sides, we get t equals the square root of 2d over a. So that's my formula. But it's this formula. It's distance equals 1/2 AT squared. That's the formula. Try not to make it more complicated. A lot of times it's just easier if you just plug things in and solve. So maybe you don't want to always go through and do what I did here to solve it, but that's what we're going to be using. Okay, so here we go. We got the square root of 2 times the distance was 6 meters. The acceleration, of course, is 10 meters per second squared. So we get 12 divided by 10, which is 1.2. 1.2 seconds squared, square root of that, and you get 1.1 seconds for my final answer. All right, that is the last of the examples. So why don't you guys go ahead and work through those problems, or you're ready to work through them in class, I guess.